Hi, welcome back to our lecture, blockchain-based software engineering or systems engineering. Last week we covered Hyperledger, and now we move on to another enterprise ledger or consortium blockchain. It's Corda. We already mentioned it briefly, and I have to admit that last year I really only had a very shallow understanding of Corda, and since it became more and more popular, we set the goal to also cover it down by lecture. Today I will give you an introduction to the Corda basics. This is essentially what I can explain to you with the help of Gonzalo. Gonzalo is one of our PhD candidates. He's also on the line with Uli. Gonzalo, say hello. Muted.
Yeah, I'm careful with the microphone. Yeah, hello, my name is Gonzalo, and yes, as Professor Florence says, I'm doing my PhD at CEVIS, and I'm very happy to join you guys today.
And he's actually applying not Corda, but blockchain-based technology at BMW. And that's also linked to differential privacy. Yeah, so it's a strange combination. But again, one of the important topics is more or less this tension between that you want to have a shared consensus about a shared set of evolving facts, but essentially among the right people. Yeah, so that you want to make sure that not all information is an unnecessary spread. And that's, I think, again, what we will see is one of the driving forces behind the design of Corda. It's much closer. It takes a totally different tack, I would say. Or not totally different. It takes a different tack from Hyperledger in the sense that it tries to stick a little bit closer to this idea of having unspun transaction output. Yeah, so that you have the idea that the transaction takes input and it produces output, which is more or less what we have seen with the read sets and write sets of Hyperledger. But and then you want to have this one goal that it creates write history in the sense that you don't have cycles in it, yeah, so that you don't write results that somebody else then reads, and so that you have in the end a linear execution order, like a transaction manager does this, which is very important that you don't spend money twice, or if you do counting, you count the right way, etc. Yeah. So that's one integrity constraint you want to achieve, which is more or less the temporal consistency of the evolution of this shared set of facts. Yeah? And the second point is the idea that you have constraints on data. Yeah? And typically we all perceive databases as writable variables in a register, like in a computer, that you can read a register and you can write a register and you override it. But if you go to functional programming and to monads, they think in a different world. Yeah, they say essentially there is no mutability. So each value you're reading has to be created by somebody else, and which creates now this long chain of information which starts somewhere from, let's say, constant values or user inputs, and then based on this you compute new values and new states or new descriptions of the digital twin, but they are immutable. Yeah? So once you create an information like an unspent transaction output, you can use it again for another computation, so you cannot more or less revise the history. Yeah? You get a history of states and state transformers, yeah? Like the monads. Yeah? So that you have functions which work over these data structures, produce new values, and again, you repeat this process. Okay, so that's more or less the basic idea of Corda, and now I would elaborate it more. Unfortunately, Corda does this not behind the scenes, somehow technically, magically, but rather very explicit. Yeah, so therefore you will learn a lot of concepts which have to work together, and it took me most of the time to get a conceptual understanding of how all these concepts, states, and rules and flows interact. Yeah? Let's try how far we can get it. And then we also have an important point, because it's an organization, the Corda organization, what's behind it. Yeah, but we understand more or less the business part of it. Yeah, who's behind it, what are their motivation, how centralized or decentralized is the governance, what's about the idea of interoperability. So these are things we are talking about today. And then we will have tomorrow, again, don't forget it, tomorrow at 2 o'clock, I think, we have the exercise slot, but it's not used for an exercise, but for a presentation of Dr. Kerber. He will describe his experience in the R3 consortium, to starting with Hyperledger, then they moved to Corda, and also about the difficulties they had to introduce something as complicated as Hyperledger and Corda into a consortium of insurances, more or less. Yeah? Okay, that's more or less then the topic of tomorrow. Okay, so Corda has been developed by the R3 consortium. And as an enterprise blockchain software with over 200, so it's one company more or less in collaboration with a lot of industry partners, AWS, Intel, Microsoft, Deutsche Bank, etc. And they form together the R3 Alliance. Yeah? The idea again here is to get traction, but have many people and supporters on board. Then there are some driving partners. It's a company which more or less has the core business of developing this. But again, they do this with a consortium so that the consortium can trust them more or less. Yeah? The first GitHub commit was done in November 2015, and then the system itself was introduced in November 2016, and then they turned all their stuff they have into open source software, and the white paper has been released. Yeah, so this went from a very close development to an open development. Essentially, then until 2019, there have been big releases, major releases with a large number of commits. So they're rather actively developing and expanding the system. The focus of Corda was initially, if you look at these people here, on IT players in the banking industry, but it has now been adopted and broadened to other application domains. But to my understanding, I think there's still a certain bias in the idea of having something where financial transactions, so the swap of I give you some tokens and I get some, so let's say some insurance back, or I get insurance policy back. So there's still a sort of certain focus on this kind of use cases. Okay, so these are information taken from their website. So what is now Corda? Again, now currently it's an open, or not, also for the future, you can reverse it. It's an open source project for building a distributed ledger platform with a permissioned peer-to-peer network. Yeah, that's, I think, the important point. So therefore, it's a consortium chain. You can also set up the network to use different parameters and more or less perform now the calculations. You have also a network operator and you have a network infrastructure. Yeah? So therefore, again, there is this idea that there is an organization behind it running it. Okay, so therefore the idea is now that you want to, let's say the design goals is to allow business to transact freely with any counterparty while retaining strict privacy, so that if you have classical interactions on the web, or let's say on the financial sector, you have two banks, and then they won't talk to each other directly, and they don't want to do this in a centralized database where everybody has access or read and write access. So therefore, it's still this idea of sending messages back and forth, but the messages are not so much seen as messages, which are arbitrary messages, but they are more or less operations on shared blockchains. Yeah? And we will see this, how this works later. So therefore, there's this idea of strict privacy between the involved parties. And only if I want to validate some data, I get this data, but other parties are not involved in this data exchange. It does not support a cryptocurrency, and as the same thing like Hyperledger, you don't need an incentive system with cryptocurrency, but you can also issue tokens and digital assets as one primary activity, which you would do between banks, yeah, and having digital assets which are represented like insurance contracts or payments or voting rights, etc. Yeah, so that would all be tokenized as we have seen it already with Ethereum. But the idea is that it should be standardized so that these parties don't have to develop their own algorithms and contracts, but there's more or less an ecosystem where they can build on, of standard contracts, as we have seen it also in the vision of Hyperledger or Hyperledger Composer. So that you start with a richer execution model than if you would simply send messages around on the network. Technically, Corda has also made a choice on not only the database structures or blockchain structures, but also on the programming language being used. And it has chosen Kotlin, which is a variation or a future development based on Java, which is very much in the spirit of modern Java languages, with more type inference and a nicer to read and write syntax. So therefore, this was done because most of the companies, as you know, worldwide use Java for enterprise use cases. So therefore, the step of having a developer who did previously work at Deutsche Börse or Deutsche Bank, he's more comfortable with using Java than using JavaScript. Also, you have the benefit of type checking and type inference and polymorphism, which is heavily used in the libraries to write type-safe code also at the blockchain level. Also, it's not only that Kotlin is being used for the infrastructure, to implement the infrastructure, but also if you write your smart contracts, you use Kotlin to write these smart contracts, and these are then compiled into JVM bytecode. But essentially, to do it, you really have to install a Kotlin compiler and have to learn Kotlin, which also restricts, which is good, because in a way it makes sure that more or less it's also deterministic. Everybody uses the same compiler, and you don't have to go down to the bits and bytes of the bytecode to understand what's going on, which is also important for, let's say, writing safe and scalable bytecode. Okay, so then these are a little bit, how we say, marketing slides, but nevertheless, I think it's important to say, if you design a system, what are your guiding principles? And essentially, they say we have business principles. So what do we want to achieve business-wise? Let's say from the adoption as an engineering system, we had to a social technical system. So these would be the business goals we want to achieve, or not goals, the principles. So we want to say so the goal was defined here. We want to have a enterprise-grade distributed ledger platform. And now, obviously, there are different ways to achieve this. And they say we want to be explicit about our principles, which should guide the initial development, but also the further evolution of the system. So therefore, we have business principles and architectural principles. That's more or less what is more or less from the business perspective we want to achieve, and this is how we want to achieve it technically, or the sometimes called also non-functional requirements. So therefore, one assumption was that they said we want to have an assured identity because, as you know your customer and all this verification in banking is very important. So trust is based on the identity. You want to know whether you interact now with Deutsche Bank, or you interact with Florian Mattes, or you interact with a GmbH or a certain company. So they say this is important. We don't want to have pseudonymity. We want to go for assured identity. So the identity of our participants is verified. The second point is inclusion. The idea is more or less that there is some way of finding other partners, something like a directory, a membership directory, which allow to participants find each other and transact with each other freely. There's identity management a little bit, so which we have also seen in Hyperledger. So then we have this privacy idea or goal to have access control and transaction details. How far this goes, one has to see later on in practice. So it's a driving force. If we can make something private, even if it costs a little bit more effort, let's do it private. Instead of saying, no, we assume that everything is public, and that's more or less a benefit also, that transparency. We also accept that there should be private transactions between parties. I think the important point is that, okay, there's again an A too much. We should delete it. That we have shared logic, so that you have a common programming language to define contracts. So that's important, that you have a shared logic and not like we have seen it in Hyperledger to say, essentially, we don't care what the code is doing. It's some code which creates read and write sets, and how these read and write sets are computed, whether they are computed by recursive functions or by loops or by rule engines, we don't care. Here, the idea is the logic should be understandable. It should be written down in a language other people can verify. This leads to the decision of having one common language. So then the code itself should not be like in Hyperledger something like in Ethereum, something where you only get the bytecode, but you also want to get access to the source code, which would then be the basis for legal disputes and assigning something. Again, you have this idea of blockchain, so therefore you want to have authoritative version of all information on the data in the blockchain. It should be immutable, obviously, and then they have this word open. I think you know it maybe from open standards and open governance and open participation. So the idea is there is a club, more or less, which it does it, which more or less defines, let's say, the JVM, or which defines the Java libraries, but they are open source. Everybody can see how it's done and also contribute proposals for enhancements, etc. That's the goal, more or less, a principle. Whether they really implement it at all levels, I think you have to then check it. But that's what they commit themselves. The second point you already read, maybe while I was talking, are these principles that it's very important for them to have a scalable system. Again, making maybe some compromises because the scalability is very important. To have billions of transactions daily, that's taken from their website. I didn't measure it, how far they are right now. But it's, I think, credible if you look at the implementation, because you do a lot of explicit design and you don't assume some very smart machine like you have with Ethereum, a single computer. Then there's also this idea of evolution. So the design should be done in a way that Corda can evolve, so that more or less allow more or less different versions of Corda to cooperate, to coexist, so that the whole network is not frozen to one very stable state, which ensures, let's say, verifiability and simplifies the whole development, but you also want to accept change as one principle for long-living systems. Okay, then you have security. The idea is, and it's not really, so you always assume that the other parties might be malicious. So therefore, the building blocks of the software always do a lot of checking of the incoming data, etc. The same thing with stability. So you don't assume that the parameters were the right ones of the other parties, but there's a lot of double checking and failure safety and redundancy to make sure that the network also works if some of the partners in the network by accident or deliberately does something wrong. And then I think a very important point that they want to have interoperability like open systems. I think that's a lesson learned from the internet, that you want to have more or less standard interfaces and industry standard tools, so that more or less one thing developed by one party can be used by the other parties. The code can be used, if you write interfaces, they more or less with the same signatures, they can interact. That's important. Okay, I think so that's more or less the idea, that you have multiple applications, multiple products and services, which based on these open interfaces can interact. So that there's some kind also of competition between the tool vendors and products and libraries. In order to establish this, we have now this open source layer, which more or less defines where you have access to the information. And then you have this governance layer, which is the Corda Foundation, which is a commercial entity. Here it's written it shall, so it should not be a commercial. So it should not be one commercial entity which controls the Corda network. On the contrary, the governing entity shall be a non-for-profit entity. And again, the problem with non-for-profit, you know it with the World Health Organization or UNESCO, etc. So in the end, if you have an organization which is not for profit, somebody has to sponsor it. So therefore, in a way, it's still, I would say, it's commercial. Because in the end, it's all about money. Because if you do something, it costs money. But the idea is not to have one central company which more or less tries to maximize their profit, but it's a cooperative where a lot of people pay in. And also this non-for-profit organization also has to run, it has to consume energy and people, it has to earn money, but the amount of money it earns is limited by the participants, by the benefit of the participants. And that's this idea of cooperatives you often find in cooperative banks, in cooperative Wohnbaugenossenschaften, cooperative associations, which more or less build houses for the community members. That's the same idea. Yeah, so they need to have money to build the houses, but they try to minimize the overhead for management and etc. Yeah, so therefore that's the Corda Foundation. Okay, so therefore the foundation consists of a governing board of 11 directors, a technical advisory committee, a governance and advisory committee, a network operator, which more or less is the infrastructure community, which more or less runs the infrastructure and gets paid by the foundation, and they are then doing this on behalf of the participant community. Yeah, and participants are then the banks or whoever wants to run Corda applications. Okay, and they earn money on a running basis by paying a participation fee to be a participant at all of the foundation, which is more or less operational costs, and a transactional notary fee on a pay-per-use basis. Yeah? So that more or less you have these two influence factors of earning not revenues, but more or less getting fees to run the business, more or less. Like the state taxes people to do the services for the state, but it should be not for profit. Okay, so the first important point is it's not a blockchain-based system, so the transactions are not put into blocks, and the blocks don't play an important role. It's all about the states which are passed along, yeah, and so therefore these states are individual objects which don't need to be assembled to blocks. We always spoke about this idea that nodes should be legally identifiable, not only technically identifiable, so that you can do these things like know your customer processes, yeah, that you can associate, let's say, a company or a legal person, and you know, let's say, how old they are or whether they have been involved into criminal activities in the past. So these would be all things they demand from their partners in this global network members directory. These nodes then form a peer-to-peer permissioned network. Yeah, peer-to-peer. There's no master and slave, or I don't know what's the current best word for master-slave relationships, but it's a peer-to-peer network where all nodes have the same rights. The communication is purely direct. We don't have this gossip protocol where changes are spread to all neighboring partners until they reach the whole network. So the idea is if two parties want to interact, they have to explicitly do a process protocol that these parties can interact. If you have a larger network of partners which participate, we don't have examples for that in the code, but then you also have to orchestrate which partner gets involved when. Yeah, so therefore there's no automatic broadcasting or gossip protocol. Again, the system doesn't assume some centralized CPU which executes it, but like Hyperledger, it assumes that anything can happen in parallel. So therefore, if two banks in Asia do something and two banks in Australia, it's unlikely that they have to talk to each other. So therefore, they can execute the things in parallel. And only if the long-term effects of these transactions somehow come together, let's say there's some amount of money collected in these different areas needs to be exchanged, only then more or less the final results then would interact directly, and given the rules of the network, we can execute, get a serializable order of all transactions worldwide. Yeah, this has the benefit of horizontal scaling, yeah, because we can do a lot of things in parallel, assuming that hopefully they don't interact, and they can be done in different nodes without either node being aware of the other's transactions. Okay, so therefore we don't have a global broadcast or a central ledger that is shared by all participants. Yeah, so therefore you get a lot of state objects which are exchanged between the parties, but they are not consolidated physically into one chain of blockchains. It's more or less a network, more or less, which is distributed. So which leads then to these private transactions. Okay. So again, we summarize it again: no blockchain, no global consensus algorithm or mining. So we have, and as I mentioned, we have now the ledger is defined as so-called immutable state objects. Yeah, these, if you program with React, for example, or you did monadic programming in functional programming languages, you know this. You more or less mute, if you want to describe a state, let's say of my laptop, you would say there's the current state of the computer, which has the following values. And then if I would switch on the computer, I would create a new state which contains millions of very similar state objects or values like the old computer, but some of them have changed their values. So therefore, you always copy more or less immutable objects, or you link these immutable objects to create new state representations. And only and then you can decide whether you want to work in the current with the current value, the unspent transaction output, which is the current value, or you want to work with values in the past which have already been because there should be only one future. So therefore you can work with the current state of the system, which is the unspent transaction output in the Bitcoin model. And also what's important, that these states are atomic. So therefore these states, you don't have the fragmented state. So therefore the state object more or less captures everything that is relevant for these interacting applications. Okay. And again, so that's more or less this idea of how to represent state. And then you also have this notion of trust, in the sense that you want to say, like in Bitcoin, that I agree that this transaction will can be executed. And also after some things have been executed, if somebody wants to sign it, that something was correct, signatures are being used. So therefore, these transactions must be signed by a notary cluster to be included in the ledger. So the idea is now that we have two rows or several rows, which we come later to. It's the parties, it's the nodes, and it's the notaries. And they have now different tasks, and I'll talk about more their tasks later on. Again, the notion of real smart contracts, they call it smart contracts, which are pure functions that verify the transaction. So the idea is that if you want to do a computation, essentially a computation means that you have an old state and a new state. And now you can define functions which verify that the new state has a correct correct characteristics, or that the transformation itself has the right characteristics. And so therefore the validation more or less of a state transition, so you have more or less not a global contract, but you have a lot of functions which are then applied by the parties to validate that the state transitions that are being executed conform to their requirements, their expectations. And so therefore you have a separation of states and contracts, and these contracts are functions which validate the states and the state transitions, that they are valid from the perspective of the contributing parties. So therefore, it's not rules. It's not a rule-based system. That you would write declarative rules, but it's really functions which check something. So what was the transaction? What were the parameters of the transaction? What was the old state? What's the new state? So therefore, you can define rather complicated dependencies on the state interactions. And so this is more or less the idea how you define smart contracts. They protect your state objects. Are there any questions so far?
Yes.
Yes.
Questions?
Gonzalo, go ahead.
There is
yes.
one.
Oh, okay.
Oh,
Go ahead,
sorry.
Gonzalo.
So there is one question. So the question is it possible to interact between entities without CorDapps? Meaning, can somebody maybe send a message to somebody else without using a Cordapp?
In the sense, like in Ethereum,
Like
that I
in
can send money
Ethereum.
to somebody else?
Yes.
No, to my knowledge, it's the only way is more or less in writing Kotlin programs, and the side effects of the Kotlin programs are the things you want to do. So I'm not aware of. So I'm also not aware of query functions in this sense. So the tutorials I have followed focus on the transactions. They don't make this distinction between money transfer operations or pure query functions.
Yeah. from that, there's no more questions.
Okay, so then I go on. But again, so there's a lot of open, unexplained things. So that was the big picture, more or less. Yeah. So what were the principles? What are the goals? Where is it different or similar to other blockchains? So now I want to go down the system architecture. And again, what we did is with Susanne and Gonzalo and a little bit of Uli's help, we went through the documentation, and I asked stupid questions until I had the feeling that I understood it. So that's more or less what I would want to explain to you now. So again, I think, so this is again marketing slide, but I think it also is important. So this idea of so that we have talked about public blockchains, where the idea is there's one global ledger and everybody's interacting with the global ledger, the Bitcoin ledger or the XY chain or the Ethereum blockchain. Yeah? There's one blockchain. Or if we would talk about other applications, might be a directed acyclic graph, whatever. Then we had a lot of blockchains which have been created for different purposes independently, where some consortia created their blockchains, let's say a Hyperledger blockchain here and a Hyperledger blockchain there, for their purposes, more or less. Yeah? So based on the blueprint, how a Hyperledger blockchain should look like. And then the idea of Corda is to say, oh no, we want to assume sooner or later, if you look at the banking market or in the insurance market or trade financing market, whatever, they sooner or later will later on will be combined. Yeah. So therefore, we want to have interoperability. So we built a system that people could create such islands more or less initially to work with each other, but later on it should be done in a way that these bubbles more or less can merge again to a larger consistent network. Yeah, and that's the idea of this global Corda network. So that initially already they say, okay, the ultimate merger will be there's not two internets, but there's one global Corda internet. Yeah, so it's more or less this idea of the global Corda network. So therefore, in order to achieve this, you need now a standardized set of interfaces for contracts that are included. Yeah, so therefore, you need the interfaces here, the standard, how the data is represented, how the contracts are represented, how flows are represented. Yeah, you need these open standards. But then you also need this additional feature of identity management, so that you can make sure that this node is not replicated 10 times. Yeah, so therefore, you want to make sure that they have unique identities. And that more or less also the notaries you have here and the notaries you have here can work, coexist, more or less. Yeah? That's more or less the overall vision, more or less. So if we then go down, the idea is more technical, that you would have now nodes, now named Alice, Bob, Carl, Demi, Ed, and some permissioning service, which more or less assigns certificates, yeah, like the membership directory, as we have seen in Hyperledger, which more or less makes sure that not arbitrary nodes can enter the network, but only a permission set of parties can enter the network. So each of these nodes runs an instance of Corda and one or more CorDapps, Corda applications, which are deployed on these nodes, as we've seen it with Hyperledger. The communication, as we said, is point-to-point and encrypted using transfer level security. So therefore, Bob, if Bob wants to talk to Demi, they more or less directly communicate, and they don't depend on a hopping protocol more here. So therefore, we don't have no global broadcasts. There is something which is called lazy propagation. So the idea is once Bob and Demi interact, and potentially they depend on results which further previously have been computed by Alice, they might get transitively access to these information. They are then broadcasted, but only not broadcasters. They are also included in the state graph, so that Bob and Demi more or less also can refer to a limited degree on information which comes from other parties and not only from them. Again, each node has a well-known identity, and the network map service maps the identity to an IP address. Yeah? So therefore, you would not identify this, use this IP address technically, but you would say this is Deutsche Bank or Demi, and based on membership lookup, you would then get the current IP address. And that allows you to do some node discovery to say, okay, I want to now get Deutsche Börse, or let's say find out where this peer is running. Okay. Yeah, and again, since it's the permission service is important because if you have certificates which you have to present to validate your identity, it's something like an Ausweis document, a certificate which essentially says the permission service, this is Alice, and Alice says this is Bob. So therefore, you can also more or less use this signing of a certificates to more or less validate the identity of other people. Again, the important point is that this is also a critical point here. Yeah, it's a centralized thing, which maybe people which are decentralized fans would say this is very difficult in the sense, yeah, because it's a very centralized notion. Yeah, so if this would go, if you would more or less do bribery with this permissioning service, there's a lot of trust in this permissioning service here. Yeah. On the other hand, it's very important from a legal perspective because more or less here you can also invalidate certificates and throw out people out of the network. So therefore, this is a thing we also find in the internet if you talk about certificate management. You have blacklists and whitelists, or permitted parties and no longer permitted parties. So to make sure that this network can be more or less governed, more or less, through the Corda network governing board. Okay, this is more or less a conceptual class diagram, and everybody who knows me knows that I like these conceptual class diagrams, yeah, because they allow you to more or less provide in one, very precise notation the key concepts in a certain domain. Yeah, if you want to understand a new domain you are not familiar with, the typical thing I'm doing is I'm starting to draw these diagrams. Yeah, if I want to understand the law, I talk about the concepts in law, what are judges, what are courts, what are relationships between courts, etc. And the same thing I did now for the Corda network, that I read the papers and I asked Gonzalo and Susanne millions of questions about what are these concepts meaning. Is it a synonym or is it a new concept, and how are the relationships between these concepts? And this is the way you build up knowledge. Obviously, if you only see the conceptual class diagram, it's hard to understand, but once you understood the concepts, it's a very good way of memorizing and also asking questions and finding out details. So again, we talked a little bit about this client layer, so who's using more or less the system. And technically speaking, we now already talked about the Corda Foundation, which is a legal entity. We talk about organizations like Deutsche Bank and Deutsche Börse, which can be clients of the network, but you can also have individual users, which are valid clients. So also as an individual user without a organization ID, you can get more or less, can be seen as a legal entity which can transact through the network. So therefore, you now have this superclass legal entity which can be specialized like this. Each legal entity can now run multiple RPC clients, remote procedure call clients, which is a standardized way of interacting in this language, of your choice, more or less. So here, this is a remote procedure call client. So therefore, you can write the clients in different languages, but the code is written on the network, on the Corda network. So therefore, if you want to interact with the Corda network, you do remote procedure calls to a Corda node. So and you can use multiple of these clients concurrently as one entity, but each of these clients can only run on behalf of one legal entity. So therefore, these cardinalities tell you a lot about the constraints, that it's always clear who did some request, which legal entity. So later on, if you look at the ledger, then you always know which legal entities did what. Deutsche Bank sent money to this user, or the Corda Foundation signed this contract, etc. Then you have, this is more or less the client perspective, the people using the infrastructure, and then the blockchain, like a database or like a middleware, is an infrastructure. So therefore, you now have things which are built, are the elements of the infrastructure. We already talked about these Corda nodes. And these Corda nodes are these technical things which are running processes, more or less. Yeah, so these are processes which are deployed on the network. These processes are operated by a network operator, and the network operator itself is a legal entity. And that's more or less a special role here. Yeah, so that's more or less these network operator nodes. The Corda nodes are essentially the parts through which you would trigger your execution of your smart contracts, or you want to do your transactions. And these transactions are not triggered as transactions, but they are triggered as flows. So the idea is now that the central concept, what you're thinking about, what the network is doing, that parties initiate flows of interactions with other legal entities, which are then called subflows, and then they use signing procedures and committing procedures to agree on the execution of certain actions. So therefore the flow does several things. A flow more or less collects information from the parties. The parties then perform computations, and then the flow also coordinates more or less that the signings of the parties takes place, that the transactions, that the contracts are executed, which validate the state transitions, and only if everything worked well, the flows would terminate, and then we have notary services which make sure that the temporal constraints are ensured. So therefore, the key idea how you interact with the network is not by submitting individual transactions, but by submitting flows which coordinate state changes, but also signing procedures in a very explicit way. So that's the important point. The abstraction is not submitting a transaction and signing a single transaction and then it runs, but initiating a flow which then collects signatures, which then does transformations, which then verifies interactions, and once everything was successful, commits it to changes in the network. Okay, that's more or less your block box perspective. So we also see now that we have now an abstraction which is called the Corda network, which consists now out of all these Corda nodes, and at least one of them. And each Corda node belongs to either one or multiple networks. So that's also an important point. You can imagine they have these different networks, layers more or less, which exist, and then they first can be created decentralized, and then nodes can become members of multiple networks. And then there's one global Corda network, which is run by which is owned by the Corda Foundation. And the other Corda networks, which are not global Corda networks, are called local Corda networks, as the name implies. Each network now has to have exactly one network map service, which more or less knows which are the members of the network, which are the participants of this network. And it has exactly one permissioning service, and it has exactly one notary service. And one Corda node can now interact with multiple network map services, multiple permissioning services, and multiple notary services. Maybe the cardinality could be 1, the minimum cardinality, we could check this. So because they should be connected to one of them. Because the Corda network belongs to at least one network, so therefore there should be also at least one network map service available. But this complicates a little bit the affairs, because it's not really so this idea that later on multiple networks coexist and one node is member of multiple networks now also requires a little bit of care if you exchange information between nodes, that these nodes and the states have to explicitly say to which notary services and map services they belong. We will see this later on. So that's a basic assumption we have to understand. Okay. I think this is more or less the big black box picture of the network and of the, let's say, the context diagram, which are the actors, here the nodes, the legal entities, and this basic concept of a network on these distinguished services. Are there any questions so far?
So there is one that is interesting. The question is, an outsider can only interact with Corda network via RPC calls.
Exactly. So that's the idea. that the interaction with the network doesn't take place, that you look at here the Corda nodes and the content here, but you look at the RPC client. There might be, so I could also imagine that there are ways more or less to ask queries to some of these nodes, but I didn't see examples of that. Yeah, we only saw transaction. I only looked at transaction code, which has to be initiated by flows. Maybe you can add to this, Gonzalo or Susanne.
I agree with you, and true, we haven't looked into any other example. We haven't found any examples where you could actually query the nodes.
Yeah, because the nodes, I think, if you look at the states, have a very complicated structure. So it's not like relational tables that you would directly look at them. Okay?
Yeah. So aside from this one, there is no other question.
Okay. Do the students hear you, Gonzalo, or do I have to repeat your question?
No, the students.
I think they hear me.
The students hear Gonzalo and see him, and I think should be fine. If there's some technical issues with that, just let me know and I'll fix it.
Okay. Okay.
There are like a couple of questions that just popped up out of thin air. So we have one that is that the Corda node is running on the local machine.
No, so the Corda node, so the RPC client would be something you could start on a laptop if you have the right permission, more or less. Yeah, so if you have more or less, if you can have the right signatures, but then you would submit it to the Corda node. And that's essentially the Corda node. You can imagine something like a how would you call it? It acts on behalf of the company. Yeah, so because it's more or less like an agent, yeah, which more or less is installed to work on behalf of the company and to do the interactions with the other parties. Yeah. So therefore, the nodes are more or less the backend parts, and these would be somehow client parts, which so they are constantly running, and they are only running once you want to start a flow.
Yeah. All right. So aside from this question, there is none.
Okay. So now we find. So we talked about the word of the entities. Now we go one level down and say what are now the data structures or data stores. Yeah. So therefore, Corda uses the word vault as more or less. So a vault is something like an address space or data container. Which can be used for information to exchange, which can be shared between peers. Yeah, so therefore, there's not the idea of one big homogeneous store like we have seen in Ethereum, or like also Hyperledger did, yeah, because Hyperledger had this one big fabric with a big table of keys and values, which was then structured into channels. But here we have this idea that you, from day one, you think in terms of vaults, so that if you create an object, you have to say in which vault it should exist. Yeah. So therefore, a vault is an accessible subset of the information on the network. Yeah. So now we have nodes in the Corda network. Alice, Bob, Carl, Lisa, and they are nodes, and now they have intersections. Yeah, so therefore Alice and Carl, so they share more or less the object F in this vault between Alice and Carl. Then there is this vault which is more or less shared now. Also, this part of the vault which is shared between Alice and Lisa, D and E, and then there's an object C in a vault which is shared by three parties: Alice, Lisa, Bob. Obviously, you could also create a situation where all of these parties will use a big vault. Yeah, so maybe so you could overlap this even further. But the idea is you would only do this if you have information which would be shared with a lot of other parties. Yeah? So then you would create vaults which have not only 2 or 3 members, but hundreds of members. So therefore, in the end, this means that more or less information is not, let's say, if the information like your state objects A, B, C, D, E, and F is physically distributed. Yeah, it's not one big address space in which it's existing. Okay. So therefore, the Corda ledger they call it subjective. I don't I don't know. It's the word they're using. So therefore, from my perspective, I see now certain informations, which is more or less subjective. That if I would run a piece of code on the Bob node and a piece of code on the Alice node, they might have a different environment in which they are being executed. Yeah, it's not the same. It's not the same fabric like we have seen it in Hyperledger. So therefore, there's no notion of a central ledger. And each node on the network maintains its own vault, its own set of facts. So therefore, Bob maintains its own vault, which is local, here A and B, and it shares a vault with Alice, which also has an own vault, but also share vault with C. And if objects are now have a certain identity and they are in the shared vault, you also have this identity, more or less, of this object is make sure that whenever you read it on any of these machines, you get more or less the same value. Yeah. So therefore, if you look at the table, so if you see the table of the data accessible to Alice, you would see different data is accessible to Alice than to Bob. So in this sense, it's the store or the ledger is subjective. But if you have shared facts, the system makes sure that the shared facts between these vaults have the same ID, also have the same value. Yeah. So therefore, that's the constraint. If the ideas of objects are equal, the information must be on the same on both tables, or if it's three parties on all three tables. Technically, it's also a SQL database, but obviously it has a very encoded structure. You wouldn't directly access with column names, etc. You will see later on. It's encoded state objects, and these state objects have an ID, and the system makes sure that these IDs are unique in the network. So that's more or less what the system does for you. Okay, we talked a lot about states, and states are the thingies we have shown here. These are the values you want to share. That's the information. Yeah, if an information system, it's all about information. Yeah, let's say, and the typical information we look at in banking is something like the status of a contract. Yeah, so therefore, a state is an immutable object representing a fact. Yeah, as we remember, blockchains are systems to create consensus about shared sets of facts and their evolution. So therefore, the shared sets of facts are now our states. Yeah. So therefore, a state is also a highly structured object because it captures some consistent set of things that belong together. In our case, it would be something like an IOU contract. IOU in English means I owe you some money, for example, so I'm obliged to return it later on to you. So therefore, this is a typical example you find in financial transactions, that you give somebody else a piece of paper and say, I owe you 10 euro, and you can come back later to me. Yeah. So therefore, if you want to represent the state of such a contract, it would essentially say, okay, this is more or less my object. It has a certain state that Alice writes to Bob, I owe you 10 euro, and I have to pay it back. So I don't know whether it's a date when I have to. I think I have to give you it back on the 1st of July 2020, or maybe it might be the date when it has been issued, and I already paid up to now 5 euro, and if I don't pay it back in time, there will be a penalty of 20%. Yeah, that's more or less the state both parties want to agree on and make sure that this IOU state and the money exchange is in sync, more or less. That's more or less the state. If you describe a state, you always cannot do this fully independently of the actor. So therefore, you now need first a contract reference that you say, okay, this state is not some piece of data anybody can change. Yeah? So therefore, there is additionally to the state contract reference, which points to a piece of code, which is a contract, which is a function which will be called to validate if any state changes take place. Yeah? So these would be these contracts which protect the state changes. Additionally, you want to know who is interested in this state. So therefore you have the participants. Yeah. So therefore, whenever this state is changed, the participants should be notified, and they have to agree on these changes. Yeah. So that's the basic idea. What now this combination, how a smart contract protects a state object which is immutable from and which is owned by participants. Yeah. So now you might be puzzled if this is immutable. How can this evolve? Yeah, and this is easily done because this not describes so immutable is only this state which says okay, this was at a certain point in time. If you look over time, we will have an evolution of this state. Yeah, so initially you don't have a state. Then you initially create the state by saying Alice borrows 10 euro from Bob. So therefore, she creates now, with the consent of Bob, this state object, which is immutable, that she owes 10 euro, which should be payable on the 1st of July 2020. And then at a later point in time, and this transition from no agreement to an initial agreement is then validated and signed by the parties and protected by the contracts. Yeah, that's the first state transition. Then we have a second state transition, which more or less takes this immutable value, produces a new value, which says that Alice owes Bob 10 euro. No, this should be wrong. This should be 5 euro. Sorry. No, it's okay. No, so it's still the initially agreement was 10 euro, but additionally we have the information that she paid 5 euro. Yeah, initially she paid 0 euro, now she paid 5 euro. So therefore you create a copy of this state object, which is the same like the initial value, except for this value of 5 euro, which has now been updated here. And then there has been a check that this update was valid by both parties and protected by the contracts associated with these state object. Yeah, and it's important that also this state object knows in which vault it is stored. Yeah, so it's also important that you have to know where is it stored. Yeah, it's because it's a distributed system. We also have to keep track in which vault it's contained. Okay, so I think that should explain now the story here. That we now get these history states, which more or less allow us to also monitor the evolution of a shared set of facts. So what is now a transaction? So a transaction is nothing else than more or less an operation which takes states and produces new states, or one state and produces a new state, or multiple states and does an atomic operation which converts all these states into new states. Yeah, so therefore a transaction, which is defined as this box here, is something which has to be agreed and signed by a certain number of parties, depending on the conditions which are associated with the states. So therefore, a transaction is an object, a value, like we have seen it with Bitcoin, and therefore Corda is similar to Bitcoin, that a transaction is an object, a value, which says, okay, this is the input states, and these are the output states, and this will be then later on, once the transaction has been successfully executed, a historic state, and this will be an unspent transaction output state, which has not yet been consumed by some other transaction. Okay, so therefore a transaction contains various inputs, output, and references. So references are things which are more or less referenced here, which refer to other data structures which are not muted, which are not changed. It's very important that it's atomic. So either both updates happen, so the money is transferred from Alice to Bob and the contract is updated, or neither money is transferred nor the contract has been updated. There's no inconsistency in between, and therefore it's also important that multiple data inputs and multiple data outputs can be concurrently and atomically changed. And so therefore there are two different types of transactions. I think the ones which are the most important ones are the so-called general transactions, which do things like this, which execute business logic. But then there are also notary change transactions, where more or less the notary, which is responsible for monitoring these transactions, is changed from one notary to another notary. Yeah, so this is a specific challenge, because now these notaries are responsible for managing the consistency. So therefore, the shift of a notary is a specific kind of transaction, which for which special restrictions apply. Okay, so we now focus on general transactions, because that would be sufficient if you work in one Corda network and you don't want to do cross-network and cross-vault transactions. So how does the transaction lifecycle now work? You first propose a transaction. You essentially say, this is what we want to do. This is the state we have. This is the state we want to produce. This is the state we have. This is the state we want to produce. We both agree with it, one after the other, in a certain order with a certain workflow, which is explicitly defined. And this is then the proposed transaction. Yeah, this is more or less then validated by both parties. So they sign it, and if all the required signatures are gathered, the transaction gets committed. So it's then sent to the notary, and the notary now checks whether the inputs and the don't have been spent by somebody else, and it then creates atomically the new output. Yeah. In addition to these state changes, a transaction can contain additional information. This can be, I think first we maybe talk about this, a time window. Yeah, you remember this was something we also saw on Bitcoin, that you say certain transactions can only happen after a certain block height. Here we are more flexible. We can also define a time window and say this transaction can only happen in a certain time window. Yeah, you can limit the time when it can start and the time when it should have been finished. So therefore you can restrict it to a certain time window. And we have seen examples of this in Bitcoin, why this might be sensible for the parties to agree on such time windows. It also can force the other party to do something in a limited time, which is also important, that you can also express obligations. Yeah, you have to sign this, or something has to happen until then. Yeah, or something cannot happen before that. Yeah, so these are things you can associate declaratively as values with a transaction. You can also associate, or you have to associate, a notary with your transaction. And if it's notary change transaction, you also have to associate two notaries, obviously. Yeah. And the notary is more or less the party which is responsible for do the concurrency control here. And then you can also have additionally commands which are executed with this transaction. But we won't cover this in the later parts. Okay, I mentioned the role of contracts. So the idea is now, if you have a transaction, this is more or less a request of some parties to do something, and now you want to protect your states with the contracts. Yeah, so therefore, essentially, to validate the transaction, the contracts now get access to the input information, and they get input to the output information, proposed output information, and then the contract can say yes, it's fine, or no, it's not fine, and I reject it. Yeah, so therefore, this is more or less an integrity constraint somehow. So therefore, a contract is now, technically speaking, a set of functions which are more or less a conjunction. Yeah, this has to be true, and this has to be true, and this has to be true. So therefore, the typical contracts consist of a lot of if statements which check whether certain conditions are valid. And they then implement the rules, more or less, how states can evolve. Contracts are deterministic, so therefore they only depend on this and on that, and potentially global variables which have to be immutable, so that you more or less can, that the contract execution, the order of the execution of these functions is not important, and also so I think that's the important point. So therefore, a transaction is valid if all the required signatures digitally sign the transaction. Yeah, so we remember there were the signatures, they have to be valid, and it has to be contractually valid in the sense that all contracts make a green light and say every input is correct and every output is correct. In the blockchain systems we have seen before, Ethereum, if we submit a transaction to the network, it's propagated through the gossip protocol to all nodes. This is not the case in Corda. In Corda, you have to explicitly say which other nodes should now get this information. Yeah, where do you want to propagate this information? Yeah, and that's rather done in a very explicit way, and this is done through flow definitions. Yeah, and the flow, as the name indicates, is similar to workflow. Maybe you know workflows from business information systems. The workflow is a thing. So one party has to do so. So let's say if I want to a workflow for getting a admission to TU Munich. Yeah, so I have to first hand in my documents, then somebody checks my documents. If the documents are missing, I get asked to send new documents. Then there's a next step. Maybe I will be invited to talk to a professor, and if the professor says yes, then I admitted to university. Yeah, that would be a workflow where multiple parties do certain things to a common end. Yeah, that's more or less a process definition, more or less, or the process execution, or mechanical process execution. So therefore, these flows are essentially mechanisms to coordinate the ledger update. Yeah. So therefore, this is done now that you submit a flow, and the flow essentially says So a flow defines what is the sequence of steps that should be executed to achieve a ledger update. So therefore, a flow definition itself is not a program that is executed. It's not a sequence of Kotlin statements which are executed, but it's a sequence of definitions of steps that should be done on the ledger. Yeah. So therefore, it's again a data structure. Also, like in the workflow definition in BPMN, is a data structure, and then there's an interpreter which takes this data structure, a flow coordinator or workflow engine, which takes the flow definition and executes the flow with the current parameters, which leads then a flow execution. Yeah. So therefore, flow is nothing else than a definition of a sequence of steps which lead ultimately to specific ledger updates. And the important point is there's no central workflow engine to which I submit it. Yeah, so instead of this, the parties themselves have to deploy the necessary flows to execute this operation. Yeah, so therefore, if Alice wants to do something, technically she can start talking to Bob, but if Bob wants to answer in a certain way, Bob has also to have a flow definition how to answer to Alice. Yeah, so therefore you have this notion of flows and sub-workflows, that somebody initiates a flow, Alice does something, and then she waits for Bob to do something, and therefore there needs to be a subflow definition what Bob should do. And if these flows and subflows are correctly coordinated, this yields then a distributed execution. Yeah, this is similar if you would do, for example, voting with Doodle. You would say, okay, then somebody has to set up a Doodle. Then the person invites a lot of people to vote. Then these people have a certain time in which they can cast their vote on certain dates. They update the state. The dates are collected and aggregated, and then a final decision is being made. Yeah. So therefore, this flow of information from me to all Doodle participants that they can vote, and that once they voted, I get notified that they voted, has to be explicitly programmed in Kotlin, yeah, and these are the flow definitions you produce. And as I said, flows typically involve subflows because the other party has to do something, and what the other parties are doing are so-called subflows. And obviously, this could go on recursively, that a subflow triggers other subflows, so that you more or less with one flow you start a large set of interactions in a network. And since the subflows are rather imperative in nature, so that they really define what happens after this step, what happens in parallel, you can more or less have a very fine-grained control how the signing process, how the committing process works. Yeah. And obviously, if you do certain things, so therefore you compose flows, yeah, so that you more or less can have sub workflows, and you can now start them, and then more or less you use them as a block box. But in order to implement them, you have to look at their internal structure and the subflows. You obviously then have a flow library for certain things like signing or committing or voting, which more or less handle common tasks. Yeah? And again, if you look at them, they're a little bit verbose and lengthy, but once you are used to this, maybe you work at a higher level of abstraction and you only read the specification, what it does, and only if you have to debug it, then you would follow more or less more closely the execution. What's important is now that one node not only executes one flow, but thousands of flow. So therefore, there may be many workflows in parallel, the same way as the TU Munich handles hundreds of or thousands of students applying at once or running multiple exams in parallel. There are a lot of subflows which are mostly isolated from each other, but sometimes they all affect some shared resource, something like a room or a set of tokens. So therefore, the concurrency control to make sure that the room is there is done then also by explicitly talking to certain coordinator nodes, which then have the necessary information. Okay, so therefore I think these flows very directly model the information or the process, both the information flow and the control flow between these parties in the network. Okay, let's look at an example first in graphical form and then in Kotlin syntax, so that you first get an idea what I've talked about graphically, and then you can more or less follow with your finger what's happening in the code. And as usual in distributed programming, you would now find something what Alice does, which more or less on the Alice node. So therefore, this is Alice and Bob. So Alice and Bob are two nodes in the network on the right-hand side. So I should move my mouse and should not use my finger. So we have now this network, and then we have two parties, Deutsche Bank and Deutsche Börse, here Alice and Bob, and they want to now create a flow between themselves. So therefore, we would now look at the life cycle of Alice. So Alice initiates a flow, which is indicated here by this dotted line, which is more or less a context. And the main task is of Alice to create that both parties should agree on ledger update. So Alice wants to create a transaction, signs the transaction, and sends a transaction proposal to Bob. And Bob would now inspect and verify the transaction with his contract and to see whether this what Alice proposes in his sense. And once he is happy with it, he would sign it. Sorry, I got a call. Can I call? Answer? Oops, sorry. So therefore, then Bob would sign it, the proposed transaction, sends it back with his signature, and then Alice could again inspect and verify the transaction from Bob and would see that it's now signed, and then she would start the finality flow, which essentially commits the update to the ledger. That's the basic idea of this flow. So, and therefore we can walk through it now. So Alice creates the transaction proposal. Alice sends the proposal with her signature to Bob. Bob inspects the proposal, verifies it, and sends it back to Alice. Alice verifies it, and then an update is done. And the important point is that the other peers, more or less, we didn't touch, don't see this update. So therefore, the information is only in the vault of Alice, in the vault of Bob. And since it contains some shared objects, they both more or less have now the same value on both sides because they signed it and they know that these updates have been done in their vaults in a consistent way. So therefore, what we have seen now is that the validity of the transaction is achieved both in two ways. First, you have rules from Alice and Bob which validate that the correct things happen. And also through the order in which these actions are executed, they also make sure that this is in a way which reaches all parties. If you do voting, it's not enough to validate that each vote only increments the counter by one, but you also have to make sure that the workflow reaches all voters. So therefore, in order to make sure that the intended semantics occurs, it's not enough to simply look at the states and say, okay, the states look right, they are votes, like we know Obama and Trump. And we have a voting transaction which increments the vote. So therefore, they only validate that the votes are incremented by one. But you also have to make sure that all voters are addressed, more or less. So that you more or less send it out to all voters. And so therefore, you have to define also the correct flow here. So therefore, that's more or less the what we call about consensus. The validity consensus is that the semantics of the operation happens, is correct. So that all transactions are accepted by the contracts on each input and output stage, and also that the transaction has all required signatures. Yeah, so that all parties, Alice and Bob, more or less at the end signed it. A second point is uniqueness consensus, they call it. It's somehow this temporal consistency, what I talked about. The idea is that you want to make sure that none of the inputs to a proposed transaction have already been consumed in another transaction to avoid double spending. Yeah, and this is the task of the notaries, because they have to make sure that these parallel transactions which are happening don't inadvertently double spend or double use the input that use as an input and output from another transaction. Okay, and that's more or less the task of the notaries. Any questions so far?
Yes, so we have a couple of questions that are very interesting. So for starters, we have one that is asking whether the IDs within a vault are, if the IDs are unique in the whole global Corda network.
To my understanding, yes, because that's the basic idea that you want to make sure that some piece of information is not replicated. So that you don't duplicate information, but that you more or less say, for each state, there should be only one representation of this state and not multiple copies of it. Yeah, and so therefore you have to uniquely identify these data objects.
I would say that is valid for within one vault or within one business network, but for the entire, I think the IDs don't need to be unique, because you don't have to have the same ID if you are in different business networks, I think. Okay, so the next question is...
then this is identified with a notary? Because in the end you want to verify.
So you have your vault, and somebody else has another business network has another vault. So there is no need for the IDs to be unique within the entirety of the whole global network. But within your own business network and vaults, the IDs should be unique, as you said.
Okay.
Okay. So there's another one. Somebody would like you to explain better. Let me see what it was. Slide number. Yeah. Could you please briefly explain the example diagram on slide 17 and what is IOU and cash transactions?
So the idea is, so IOU, as I said, is a representation of a state of a obligation that you said, I'll give you, so you lend me, so Alice essentially said, I owe Bob 10 euro. Yeah, so that's more or less a paper she wrote, she signed. Like if you take a credit from the bank, yeah, you owe the bank money. Yeah, that's the basic idea of financial transactions. You get money from the bank, and the bank tells you, okay, Alice owes to the Bob bank 10 euro. Yeah, that's more or less your obligation here. And then now you want to pay 5 euro of your 10 things back. You want to more or less return a part of the money. So therefore, you now take your cash, which describes, you have a contract which describes the money you have. Yeah, you are the owner. The currency of your account is 5 euro. And now you want to deduct 5 euro from your account and create new cash, which is now owned by Bob in euro with 5 euro. So therefore, you more or less deduct more or less cash from your account, and we transfer the ownership of these 5 euro cash, this unspent transaction output. You more or less change the ownership to Bob. So therefore, Bob gets money, but you want to make sure you only give it to Bob if Bob promises or guarantees that the IOU is correctly updated, so that the amount of 10 euro is reduced to 5 euro. And this is more or less the transaction, which essentially is saying move cash to Bob, and Bob will in return update this contract state to reflect that you only you already paid back 5 euro. Is that now clear?
All right. Yes. All right. Thank you. I have another question for slide 20, just for clarification. There's a student that is asking, shouldn't be a notary be involved in slide 20?
Yes. Yeah, that's more or less. I first want to talk about the flows, and then we talk about the notaries. Yeah. So I left the notary out. That comes only at a later stage that I also involve notary in the code.
Mm-hmm. All right. And then the last question, does the start finality flow only update Alice view?
No, again, we will see this later. So this was the idea that we only talk about agreeing on the ledger update. Yeah, so that was up here. Essentially, both parties said, okay, we now all agree. And then the notary would have to do his work, and then we would start a finality flow, which would do the update. Yeah, and this I again left out like the notary.
All right. So there are no more questions. Oh, there's one, but I will maybe come to that one later.
Okay, fine. Okay, now we can come to the notary cluster. And as I said, the notary is responsible for this uniqueness consensus. Yeah. So a notary cluster, as we have seen, is so. So there are three words now. Initially, we talked about the notary. Yeah, there's one notary doing it. Maybe if you go back. So there's one notary, but technically speaking, it's one notary service, which may be implemented by a notary cluster. Yeah, that's the important point here. Again, for redundancy and failover things, this would be a service which is done by a cluster of machines. Yeah, as we have seen it with Hyperledger also. Yeah, so therefore the role of the notary, as I mentioned, is to ensure the uniqueness consensus that. They validate more or less that the inputs are not double spent. The unspent outputs are not only used once. So therefore, they do this by not sending a message around, but they sign again the transaction. Yeah. So therefore, the transaction is. The transaction is signed by the notary. Yeah? So that's the idea, that you always have objects, and the object itself contains the necessary information so that other parties can now look at all the signatures and can understand the status of this transaction. So therefore, you now have a signed transaction by the notary. The other idea is that a notary would reject a transaction and flag it as a double spent attempt and more or less reject it. Yeah? So that's the other action that could happen from a notary cluster, that it more or less rejects transactions which would lead to a conflict. Again, rejected transaction like in Ethereum or databases can be reissued because it was not a logical error. There was no attempt to create money out of thin air or to cheat in the IOU transaction. So it's consensus, it's a valid transaction, but unfortunately it has been executed in an order which is not serializable. So therefore it has to be re-executed. Yeah? In order to do this, notaries maintain a map, which are now mapping from the ID of a transaction and the requesting peer to a state which marks it more or less. Yeah, so we have a key is a transaction ID and the output index, and the value is a transaction ID, the input index, and the requesting peer. Yeah, that's more or less this mapping. Yeah, you remember this network of unspent transaction output in Bitcoin, where more or less we have to keep track which input is used by which output is used by which input index. Yeah, you remember in Bitcoin we had the transaction ID and its output on the left-hand side, and then we have the consumer transaction, which has also a transaction ID, and then an input index, and the peer that wants to consume it. Yeah, that's more or less the data structure which the notaries use. Each state has an appointed notary cluster, so therefore a state assigns directly points to the notary cluster that should validate it, yeah? Which makes sure that it doesn't float around between different clusters. Again, like we have seen it with Hyperledger, they are pluggable consensus algorithms which can choose about different ways of more or less doing this mapping. But again, I don't go into the details here, and I could imagine that most of these systems run on a very default consensus algorithm. Okay, now we want to continue based on your questions. Now we include also the notary cluster, and we also go explain more in detail what the finality flow does. These were your two questions which you had. So therefore, we now agree on the ledger update, and we continue this. So we have seen Alice built the transaction, signs it, Bob inspects and verifies it, and signs in the case of success, this is the happy path here, sends it back to Alice, she inspects and verifies it, and starts the finality flow, which is then initiated, which now goes to the notary cluster, which now validates the uniqueness constraint and then signs again back the transaction with his signature or her signature. I don't know whether it's a male or female notary. Again, now Alice records this transaction in her ledger, and Bob records the transaction in his ledger, because they now know that this was a consistent and final transaction. Yeah? So therefore, this is called the finality flow, which more or less tries to finalize the transaction update on the ledger. Okay. Okay, I think this was all I want to explain here. As I mentioned, we have this global Corda network, which I think maybe that's redundant here. Yeah. Yeah, maybe we repeat it here. So that's now this global Corda network. You remember we had the local Corda network, which is something I could run private on my own with my friends. But in order to be a true Corda network, I should also connect to the global Corda network so that other parties can find me and that I can interact internationally, globally, more or less. Yeah, so therefore, it's the global Corda network builds on the local network with transaction legality, finality, and privacy. But additionally, it provides identity certificates to validate that these are not, let's say, students at TUM running a Corda node, but these are real banks and real partners, so that you can rely on doing interactions with these parties and validate not only their digital certificates, but also their identity certificates, that you really know this was done by your favorite stock exchange or your Deutsche Bank. Okay, so that's essentially what I already said. And again, the global network operators run not by individual banks, but again by the Corda Foundation. Yeah, so therefore there's also some initial also money transfer necessary, which is not done on the bank and not done on chain but off chain through the contracts the banks have now with the Corda Foundation. Okay, so if you now want to look at a network, what are the parameters? We already talked about it. What are the constituents? So what are the new things more or less you get to the global network is you now have a well-defined set of network parameters. Let's say which consensus algorithm is used, which version maybe of contracts are being used. Yeah, these are global network parameters which are global to this network. Then you have this identity framework, which I talked about, which link now digital identities to identities in the sense of the banking industry. These certificates. Then you have notary pools, which are recommended to be used by the participants. There are also well-defined oracles, which provide information services like stock exchange rates, etc. I don't know exactly what the current oracles are in this network, but they also exist, and with the same argumentation that the state transformers don't have access to local resources, they don't have access to the real environment, so therefore you need this notion of oracles also in the Corda network. The global Corda network also has contracts, like we have seen them, the ERC20 tokens, for implementing the interface or for defining the interfaces and having reference implementation of digital tokens for value transfer, as we have seen it with the euro exchange in our IOU contract. Then you also have more or less this open governance idea that, if anything would go wrong and you have complaints, then you know who to call and who to drag to court. You also have this network map service where you more or less have this mapping from Deutsche Bank to the server node address of the Deutsche Bank and the global notary service for the whole global network. So that's more or less the technical system architecture. And now I want to give you one short glimpse. And again, running a little bit out of time, but we should spend this time so that you get an idea how similar to what we have seen with Facebook, with Hyperledger, how does such a CorDapp look like? And therefore, we use a very simple example. Actually, we tried to do a more complicated example, which I came up with, and then it turned out it was very difficult to implement. And again, I think the main takeaway is that this is all very transparent, very easy to understand. Not easy to understand. It's well documented. It's very consistently described, but it leads to, I would say, a big notational overhead, to do even very simple things. Maybe that's a nice way to describe it. So because you do very explicitly the things which I mentioned. It's not done by the virtual machine, with the press of a button, but you really have to model all these objects very explicitly and in detail. Okay, and we don't look at how you invoke it with RPC. With this we assume we only look now at the flow definitions and the state objects and the contracts and the transactions, etc. So therefore, again, if we have such a CorDapp, which is a Corda distributed application, is more or less this code which allows nodes to reach an agreement on updates of the ledger. And this is done by defining flows that Corda nodes owners can invoke over RPC. So therefore you trigger them with RPC, but the execution is done on the nodes who are executing the flows. The flows refer to state objects at runtime, which are based on state definitions. They use contracts, which are functions which are defined at compile time, which are stateless in the sense, so therefore the constructs are immediately executed. Then you have flows, which are flow instances, which are created based on flow definitions, which you create at compile time. And you have transactions, which are, again, operations which are defined by transaction definitions. And the execution of the transaction then does ledger updates. And additionally, you have APIs and a user interface which allows you through RPC to access more or less to submit to start flows and to inspect the state of the network in the notaries through web server APIs. Okay, and again, maybe we would have to continue this next week because that's, I think, important for the next lecture. We have these two parts, more or less. We have on the left-hand side, we have things which are done on compile time, which is a logical view, where we talked about that if you develop an application as a party, you define a package of code. And this code consists essentially of a set of flow definitions, and these flow definitions can contain subflow definitions. And these subflow definitions have also very specific semantics, so therefore you can have either 0 up to 8 subflow definitions for signature collection workflow, finality subflow, etc. They're well-defined subflows for certain purposes as patterns, which are defined with these subflow definitions. And again, this is done by code written in Kotlin. So these packages are Kotlin packages, Kotlin flow definitions, Kotlin subflow definitions, and then the flow definitions themselves define, refer to transaction definitions, and these transaction definitions refer to input states and output states, which are then transformed by these transactions. So a transaction consists of the set of input states and the set of output states. It's more or less not a piece of code, but it's a data object. And this data object is more or less created by the flow definition and is part of the flow definition. And that's all done in the compile time. And the flow definition also has contract definitions, and the contract definitions always protect, where is it now, which is missing here. So here, it's here, this link, so that the contract definition is associated with the state definition. Yeah, so therefore a state can only be executed if the contract yields true and says, yeah, this is a valid state definition, more or less. Yeah, so that's all done with Kotlin code at compile time, and then you start now, and now a party would deploy this package. That's more the owner of the package, like Alice or Bob, which is a legal entity. Yeah, so that's more or less the logical view, how you deploy your code in the different nodes. And once you start now, the flow definition is that you have now your Corda network, and now you have a node, and on this node you have now a large number of flow states, of all currently executing flows. As I said, maybe if this would be Team Munich, there might be hundreds of flows defining student applications, and each student application would have its own flow state, and each flow state might have multiple subflow states which describe how far the execution of this flow already proceeded. The flow state itself, more or less, refers to the flow definition, and then we can, through the flow state, we can now access the involved transactions, which are generated, which then have input and output states based on the state definition, the structure of the state definitions. Here the state definition would say the type and the name of the fields of an IOU state, and this would be the current state of the IO state. So therefore this would be your database essentially, and this would be your execution stack, more or less, which says what is currently being executed with sub-workflows. And all these things link back to data definitions, like here state definitions, and to code execution semantics defined by flow definitions. So therefore at runtime, this is more or less, you have both. You have the compiled packages and the execution states and the data states, which make up your whole state of the network. And again, the contract definitions are then compiled into bytecode, which is shipped in the network to protect the states also on different nodes. Okay, so that's more or less what's happening. And as a side effect of the execution of transactions, log entries are produced on the nodes, which more or less describe more or less what happened, so that you not only see what should happen in the future with the flow, but what happened in the past, which log entries have been created in the past. And the notary nodes, again, are executed as part of the network and to validate the execution of these log entries here. Okay, I think that's more or less a big view. Unfortunately, now I'm running out of time. So therefore, I'll simply show you what I wanted to present, and we will do this next week at the beginning of the lecture, that you have now these objects, and you first have to define a token state, an output token state. You have to define a token issue flow initiator and a token issue flow responder object, which all refer to token state objects with get issuer, get owner, get amount, get participants methods, which are defined by the framework. And the token states are protected by token contracts, and you have to define your own token contract based on the use case we are using, and the use case we are using is a token minting use case where parties create tokens and they assign these tokens to other parties. It's a very simple transaction which doesn't do very complicated things. It simply transfers tokens from one person, which mints a token, to one new owner. And you have to create all these objects to do this. If you would then deploy, you would see something here on your development workbench in Kotlin, that you more or less have this bootcamp code, which is the demo, with all your 4 contracts, your 4 Kotlin classes, which now implement the token contract, the token issuer, flow initiator, the token issue flow responder, and the token state, which is protected by the contract. And if you now click on the source code, you would see this in your development environment, the token state definition, the contract state definition. And as you can see, there's a lot of comments here and a lot of annotations, because most of the code here is inherited from superclasses like contract state, and then you simply overwrite existing superclass definitions with your local objects. In order to know what's going on, you essentially now have to understand the superclasses, and then you also have the token contract, which then does the necessary checks on the state changes. And that leads to more or less the token contract. And then you have the token issue flow initiator, which also does a lot of repetitive stuff for defining the flow for issuing a token. And this flow initiator needs now a second object, which is a token flow issue responder object, which also has a constructor and which defines how now the token issuer flow should be responded to by the recipient of the token. Yeah, and as you can see, if you would write this in Ethereum, that would be a very small piece of code because it's essentially is assignment of the ownership of one token to another party, with a disadvantage now that everybody can read the code, everybody can inspect the blockchain, and here the goal is to have now a very precise workflow which limits the parties to the visibility to this interaction to a minimum amount number of parties and notaries, yeah, and having a very explicit description of this. I think this should be enough to give you an idea how this looks like. There's not the time to go into all the details. I wanted to do this, but maybe I was too optimistic. We did it in just the first time this lecture. So therefore, we have to see whether we can start to do the explanation in more detail at the beginning of tomorrow's lecture. Okay. Maybe questions. We're running out of time, but maybe one or two questions we could take. Uli, you have to decide for the perspective of the students what would be the best way.
So we can
handle
answer
questions.
Two very, very short questions, and also your answer has to be very short because we're 10 minutes already over time.
Yeah.
But I'll.
All right. So let me find. Let me find one that is quick. Can a client recover past transactions, the state if it accidentally lost all local data?
Can a client? Can a client
recover past transactions? If it accidentally lost all, I guess he means also the node. So like this entity.
So essentially, I think
the
so the client is something which is temporal. Yeah, so it exists only as long as you want to start more or less the flow. You trigger the flow, and after this, more or less all the interesting things are happening by workflows which are executed on the network. And the side work, and once you submitted a transaction, you would essentially have to go to create another flow, which now inspects more or less with this brutal way. Then you have another flow which now looks at the Corda node and tries to find unspent transaction output from other people. Yeah. So therefore, there's also a major limitation which I see, that you always have to know where you get your states from. Yeah. So you have to find the necessary handles to the objects you want to consume. That was one question I also had to the developers. Let's say, how would you model objects where a lot of people have shared resources? And then the idea is that obviously you then would say there's a designated operator. We had the example of a toilet, and that this operator you have to know, and you have to ask the operator, give me this designated object I want to work on. Give me the account data of Mary. So that you have more or less then here a bank, and then you would go to the bank and say, find me the account of Mary, and then go back. But you have to know where now Mary is, and you have to explicitly look it up.
All right.
So therefore, you cannot lose it. Yeah, it's like if you would ask, can the bank lose your account? You would say, no. Even if I lost my bank transfer, the transfer would have happened, and I can go back to the bank and say, show me my current account details.
Okay.
Okay. Do we have time for another one, or should we?
One very small one, and then we wrap it up.
Okay.
Only it's the arbitrator.
So are there multiple notary clusters? So we know there could be many notaries, right? So the question is, if there are, how can a double spending be prevented if a malicious party sends his transaction to two different notary clusters?
Yeah, therefore, so I don't know it exactly. Yeah, but my assumption is we mentioned more or less the trick is that once you created a state, it stays with the same notary. Yeah, so therefore it cannot escape initial. So if you don't have notary change transactions, everything is fine. Yeah, it's a similar if you have something like in Java, you have something like a garbage collector, which works in one workspace, and then you have something like pointers between distributed Java instances. Then obviously you have to have a global garbage collector, which more or less verifies the pointers in your distributed Java network. This is what I would assume what they are doing, that they say, okay, there are these dangerous transactions which more or less move one stage out of the scope of one network to a new notary. And obviously these notary spanning transactions require certain additional constraints. But I don't know exactly how this is working. But this, since they also mentioned it initially in the definition of transactions, I think this is the goal here, to more or less allow cross-network transactions facilitated by the global Corda network.
Mm-hmm. All right, then that is all on the question side.
Okay. So I do hope you learned something about Corda. And again, we have an even better expert than me as a beginner with Dr. Kibber tomorrow. He will focus not so much on the technical issues. I think he could also answer them, but also, let's say, so how scalable is this? Yeah, because that was one of my main questions. If I have to write so much code for doing a simple money transfer, if I have a very complicated contract, I could imagine it gets very clumsy to write it. Yeah, and these would be questions I would have, let's say, from the conceptual scalability of the system. Not that you do a lot of transactions, but let's say, how difficult is it to verify these contracts and understand them? Okay, so thank you for your attention, and see you tomorrow.
Thank you very much.
Okay, this is Florian again. So we underestimated the time it takes to explain the basics. But since the basics might be relevant for tomorrow's talk, Uli and I decided that I do more now a short introduction to the last slides, so that you not only have to read them, but you also can follow my explanations. And again, this is the most simple app one could think about, or distributed app one could think about. It's token minting. So the idea is that an issuer can mint an amount of tokens and assign them to a new owner. Yeah, that's the basic idea. So we have a token, and now we don't want to talk about moving tokens around, but simply generating the initial amount of tokens and assigning them to a new owner. Oops, I pressed the wrong button. So the idea is now that we have now several token factories and several token users. And now we want to more or less do the initial step that the factory creates a token which is assigned to a user. And the whole network is governed by a notary. Yeah. And what also is interesting is that we want to not only see how the transaction is performed, but we also want to create events so that participating parties are notified about these operations. Okay, I think I explained everything here. Okay, and I think the important point is also that we want to that not only the factory has to agree that the coins are created, but also the user who gets the coins should agree that he gets the coins. Yeah, if you think about Bitcoin, that was not necessary. Everybody could send arbitrary amounts of money to your account, and you don't have to say yes or no. But here we assume that also the receiver should agree on the transaction. So what we now have is the following idea, so that in the end we want to perform the following state transition from no existing inputs to creating the initial token. Yeah, and so therefore this token state would look as follows. It's something like the constructor for a token, that it says, okay, one issuer, which is a legal entity, assigned to the owner, which is also a legal entity, a certain amount, which has to be larger than 0. And then there's a list of participants which should be informed about this fact. And there should be some contract code reference which validates more or less or protects this future state, so that if somebody else would work on this future state, also this contract code would protect this future state. And then it would also contain a legal prose reference, which we don't show in this example, which essentially would say, okay, based on which more or less legal contract is this taking place. And that's also one way more or less of tying so that would be something like a contract of a contract document. Let's say the contract you signed with the bank on that day, whatever. Okay, so that's more or less the idea that this issue command should perform this transaction. And as I said, we need now additional, so in addition to this token state definition, which essentially would say, okay, who's the issuer, who's the owner, who's the amount, these are all private variables. We also want to have this list of participants, which are then a list of abstract parties, which should be notified. Then we have the getter methods to get the issuer, to get the owner, to get the amount, and to get the participants. So it's more or less the token state in its minimum form. Essentially, it's all about the amount passed along. Then this would link to a token contract, and the token contract has this standard pattern that it has an ID, which is compulsory to identify the contract, and a verify operation, which is executed whenever a new token state has to be validated. So therefore, it gets a ledger transaction as an input, which then points to the input state and the output state. So therefore, it can now then get access to the token state. The whole thing, the whole transaction cannot be directly executed. So as we said, we have to create now a flow. And this flow should be initiated by an RPC call. That's more or less the part on the left-hand side, that you have a token issue flow, which is more or less, as the name indicates, it's a flow. It's a flow to issue a token, as indicated by the name, and also it's an initiator workflow in the sense that it can be externally called and be started. And the flow should be parameterized, so it should say who's the owner of this flow, what kind of amount should be, let's say here, initiated, and then we need to define a progress tracker, which is more or less an object of type progress tracker, which obviously informs about the progression of this flow. Let's say initiated, suspended, restarted, etc. So that's more or less a way that you can more or less observe the flow as it evolves. So therefore, you have a get process tracker method, and then you have a key method which is called call, which produces a signed transaction, which is the signed transaction, which then performs the token transfer. Then we have also, this is also one side, which is done by the owner, and then the owner wants to inform the other side. In this case, the future owner of the token about the fact that he received or she received now or is member of this flow, and therefore we also have now a token issue flow responder, which is more as the dual, because the two parties flow subflow, which will be initiated. Again, this has a call method, and so therefore it's also a flow, which all have a call method. Okay, technically, this looks like as follows. You open your Kotlin workbench. You have now this bootcamp demo project in your workspace in the Java folder, which contains Kotlin code in this case. You have this package bootcamp, and then you have these four classes: token contract, token state, token issue, flow initiator, and flow responder. And then it's test-driven. You also then have a test suite, which more or less would initiate these contracts and do some tracking, so that you can observe what's happening, that it happens as you intended it. And then there's a lot of other things around which you need to build it, etc. Now we look at the source code, and we start with the token state, because it's all about this token state. So therefore, we now have opened the token state Kotlin tab. It's part of the Bootcamp package. We import a lot of libraries, which we don't show here. And then we have the token state class, which is a contract state, is a subclass of contract state. And contract state, and this ends here. So therefore, it overrides now several methods of token state. And in order to understand, we look first at contract state. Contract state is a standard interface. It's not a class, not an abstract class. It's an interface defined in the net.corda.core contracts package, which in turn also imports several things. And it's a contract state, and it defines that there's a compulsory field participants, which is a list of abstract party, and it also defines more or less the semantics of a contract state. So therefore you can also then read what a contract state is. Then you see we have a lot of annotations here. I think people familiar with Java know this. Annotations are pieces of code which are not executed by the runtime system, but which have semantics to preprocessing tools and for tools which work on the code. And in particular, for example, here we have annotations which indicate that this should be serializable according to the Corda specifications, which can be verified then by linting tools. And then there's an annotation which I assume means that it should be used for the distributed Java virtual machine, that you more or less keep the bytecode that you can send it around. But again, this is only wild guessing. So essentially, you do monkey see, monkey do. What you get, you repeat this. Or you're curious and you look up the documentation. But again, you wouldn't change this class, because it's a built-in class of the framework. What you are now doing is you now define your constructor, token state constructor, and it gets as an argument the issuer that wants to create the coin, and the owner, which should be the future user of this coin, and the coins, and the number of coins is indicated by the amount parameter. So therefore, it's a constructor which more or less now initializes the private fields, which have the same names, issuer, owner, and amount, with the respective fields, and then initializes the participants field, which is required here, with an empty array, which is then augmented by the issuer and the owner. These are the two participants of this flow. And of this they are the participants of. That's a good question. So here it's attached to the state. So therefore, these are participants which should be notified about these state changes. And then we have the getter methods: get issuer, get owner, get amount, which return the respective fields. And then we have the get participants method, which returns the participants. So as you see, there's a lot of boilerplate code, which more or less is maybe the template you would then use more or less to define your own contract state, enriching it with the necessary parties. We are then now ready to talk about the token contract. And the token contract is, as I said, essentially a method definition, a way to define a method which is called verify, which gets the ledger transaction TX. And this verify operation should normally run through. It doesn't generate a Boolean value. So if it successfully completes all the preconditions or all the conditions on the verification are satisfied, if any of the conditions is not satisfied, you would get an illegal argument exception. And so therefore, there are a lot of illegal argument exceptions which can be raised. And the illegal argument exception gets also a string which explains what went wrong. Okay, so this looks a little bit, how would you say, overwhelming for such a small state. Why do you do so much? But before we look at the verify operation, we look at what else is the token contract specifying. First, it's a token contract. It implements the contract interface, and therefore it has to have a contract ID. and there's a naming convention. Yeah, so there's a naming convention that you could say, okay, if I want to find it by name, I can now use this name, which is consisting of the package name and the token contract string. What else can I define for a token contract? The idea is if I have a state, I can do several things with a state normally. Yeah, here I can only issue a new token, but in reality we would issue tokens, we would transfer tokens, maybe we would burn tokens, or we would maybe duplicate tokens. I don't know what. Yeah, so that would be the idea, that you now define essentially something like a state machine, that you say you have a state, and then you have operations on the state which create new states. Yeah, so therefore you would now define the possible transitions in the state machine, and here we only have one label, which is called issue, which is a command. Yeah, this is a way how you define in Kotlin enumeration types. So therefore you now define commands. And in this case, the command doesn't have additional arguments, so therefore it has this empty curly brackets. Otherwise, it would be union type, and you could also define additional fields here, which are additional arguments for the command. So therefore, the issue command is more or less here enumerated. Okay, so then we can now are ready to override the method verify, which is inherited from the contract class. And which gets the transaction, as I said, and may raise an illegal argument exception. So what we now do is we have now this transaction object. Yeah, you know, transaction is not a piece of code; it's an object, and this object has a list of inputs. Yeah, like we have seen it with Bitcoin, and I showed you on the example. So therefore, we get now the input states, which would be a list of contract states. Yeah. We get the output states, which is also a list of output states. And this is the generic structure. It's something like if you have a request handler in a web server, it always gets a request and produces a response. And now it depends what you want to do, what you expect now from these inputs and outputs. And obviously, if you have an issue operation, we now would assume that the command which we get is a singleton, as we only have one command. We don't have a list of commands, we have a single command. So therefore, we first would ask the transaction, what are your commands? And if the size is less than 1 or larger than 1, we would throw an exception transaction. The issue transaction should have only one command. So then we look at the shape of the transaction. We will say, okay, we now have an issue transaction. Therefore, we expect that the input is empty. Yeah, we don't have any input which is consumed by our issue transaction. So therefore, we must have 0 inputs. And we also expect that only one state is produced. So therefore, the output size should be 1. Otherwise, we would throw an exception and abort execution of this verify operation. So then we would look at the types of the states. Yeah, so we have an empty input state, so therefore we don't have to verify it. But for the output state, we want to make sure that the output the transaction wants to produce is not an arbitrary contract state as specified here, but it has to be, it's not an arbitrary object, but it's a token state object. So it's not an arbitrary contract state, but it's a token state object. Yeah, so therefore we make a type check here. If this fails at runtime, we would also complain. Now we are ready to do a typecast so that we more or less get now the first output and cast it to a token state object, which would succeed because we checked it. And now we are ready to now look more at the token state, which we want to produce as an output. And again, we would now make sure that the output of the amount of tokens we generate is larger than 0. So amount must be larger than 0. Then we look at the value. So we look at the first command in the list of commands. We check that there is exactly one command, so therefore this doesn't fail. We get the value, and then we verify that this is a token contract command issue command. Yeah, so this is more or less from this command enumeration the issue value. So therefore we do this comparison here. which is more or less the pattern in Kotlin to verify enumeration types. And if it's not the case, then again we will say, no, sorry, operations on tokens are only issue commands and no other commands are allowed. Then we look at the required signers. And the idea is now that we get more or less the signers, and then we look whether the signers contain the issuer object. So the token state has an issuer element, and from the issuer we get the owning key, which more or less identifies, or which is the signature of this issuer. So therefore, and if this is not the case, we cannot find the signature of the issuer, then we say the issuer must be a required signer, or is a required signer, so it's missing now. So the issuer didn't sign. The second thing is, for demonstration purposes, I added this. We also ask the owner to agree on the token creation. Normally, owners would not be, so if it's money, you would not deny that the bank sends you money. But here the idea is now we want to make sure that you agree that money is transferred to you. So therefore, we again look at the list of the signers, and then we verify that the owning key of the owner is also a member of this signatures. Otherwise, the owner we raise an exception. So as you can see, the verify operation is very similar to the Bitcoin script. Which essentially checks a lot of validations so that the outputs and the inputs have the right constraints, which you would expect. And as you can also see, this is not really easy to read. So if you go through each line, you would say, okay, this makes sense. But it's not obvious whether all the constraints are checked and whether to, and if there's a lot of copy and paste you would typically do. So this is a very error-prone way of coding, because you more or less have to go from an arbitrary command object down to very specific command objects. And obviously this calls a little bit for higher level abstractions, but again, that is not done in Kotlin. You can now define your own libraries and higher order approaches, but that's the basic way how you interact now with the Corda ledger. Okay, so this is more or less the verification and the state, and now we have to create a flow which more or less does these things which you may remember. Which more or less does this. So we now want to build this, we sign it back, verify it, and start the finality flow and get the necessary signatures also from the notary. So, and this has to be programmed again. So therefore we now have a token issue flow initiator, which is more the party of the initiator who creates this flow to issue a certain amount of coins. Again, you would say a token flow token issuer flow initiator is a flow logic, and the flow logic is a type. Has a type parameter because we know that the flow logic produces a certain result. It's a functor. It's more or less a system which more or less creates results, and the type of the result is a signed transaction. So that's more or less a way to create a signed transaction. Therefore, the type checker can more or less help us, and that's also why JavaScript, not JavaScript is being used, but Kotlin and Java, because you have now this parametric types and a very nice subtyping system. So that you more or less can more or less do this flow programming in a rather type-safe way. Again, we now have two essential parameters. We want to define that we want to, if we create such a flow, we want to define who should be the future owner of the coins and how many coins should the future owner get. And the initiator of the flow is the issuer also of the token. So therefore, the constructor more or less only gets two arguments, namely the party that should become the owner. It's an object of type party. It's a final element. It cannot be muted. It's an amount, which is also final. It cannot be muted. And then the owner and the amount are initialized. We also have to define a progress tracker. And we create more or less a default progress tracker without any further arguments. That's also a local object. And we then also have to define the getter method for the progress tracker, which returns now this default tracker. Okay, that's again boilerplate code. Now we would define the call method, and the call method has to have a result type which matches more or less the flow logic. Yeah, so therefore, in our case, it will return a signed transaction. Yeah, so flows can return different things, and depending on what they return, we now define the type here. And again, they can also throw a flow exception if anything goes wrong. And these are checked exceptions also in Kotlin, like in Java. Okay, so now we do a lot of things which are essentially constructing objects. It's not really doing something. I think that's very important. This is something like a factory. Right? It creates more or less a token issue flow with these parameters. Right? It creates more or less a script or flow definition. And this flow definition, this is a flow definition, and it initializes a flow which then can be executed. Yeah. So therefore, we would first say, okay, now we want to find out which notary should be responsible for this flow or the state transition in this flow. So therefore, we would call more or less this factory method, get service hub, get network map cache, and get the notary identities. And from this set of identities or a list of identities, we get the first element, which would be our default notary. Then we take we define the issuer is ourselves, yeah, so the party which is more or less executing the flow, which is done by this method get our identity, which is more or less initialized as a thread variable through the caller. Yeah, it's more or less like in Bitcoin, it's the caller. Yeah. So the issuer is the party which initiated the flow. Then we can create the token state, which would be the final state which we want to produce. This is the token state. Using the token state constructor we defined 2 pages ago, and say for me as the issuer, for the owner which I got as in the constructor and the amount, I want to create a new target state, which is the output state. I want to define one command, which is the issue command, which we defined in the commands enumeration of the token contract class, which gives us the command. And now we can create a transaction. Yeah, so therefore we now use this builder pattern that you have a transaction builder, which more or less creates a transaction builder, which might depend on the notary. And then we do calls to this transaction builder, which now builds a transaction. Yeah, so it's not executing a transaction; it builds a transaction, a flow definition, more or less. So therefore, we now add an output state to our transaction we are defining, which is now the token state we created here, and a token contract ID. Yeah, so because it's a state of type token contract. Yeah, this we defined as the string in the token contract. We define the command as the command data, which we defined here, and we sign it now with the owning key. Then we define that that now a verify should start after we created the transaction. And once we now, where is it now? Then we sign the initial transaction and create a new session object, and then execute or define a sub workflow which is based on a collect signature flow based on the signed transaction and the single list of a current session to create this subflow. Again, there's a lot of more or less repetitive copy and paste ongoing here, which more or less now creates the necessary subflow, which only consists in executing such a collect signatures flow for the signed transaction. And then we return now this subflow, which it executes a finality flow for the fully signed transaction in the single list of the session. Okay, so let's go back. What did we do? We essentially defined, where is it now? this part of the story. Yeah, we said, okay, we built something, we created subflow, we said now after the signing of the transaction, this should be verified. After it has been verified, it should be signed, and then it should collect now the signatures here, and then it should return the signed transaction. Yeah, so that's more or less the part of Alice. In between, she now used this responder workflow, and this responder workflow is now defined in a different class. Well, so now this was the flow initiator, which was Alice in our case on the right-hand side, and she used now the token issue flow responder workflow, yeah, which is defined here. So therefore, the token issue flow responder is again a flow logic. In our case, it doesn't return any value. It simply signs objects, so therefore it doesn't return a signed transaction, but it returns a void value because it only enriches an existing object. It's called token issue flow responder, and we want to also tell the compiler and at compile time that this should fit. Be the responder to this initiator. There might be several initiators, and we want to now bind it to that initiator, so that if now the subflow workflow is initialized or created, this issue flow responder is created. Again, we now have a constructor here, which is this object here, which now gets the other side by convention. Yeah, so therefore, if I'm a responder, I get more or less the other side, which I should respond to. That's more or less my main argument, which I get. I remember the other side, so that after I have done my work, I can transfer control back to the other side. Okay, so therefore, this is now the definition and the constructor. And if now my sub workflow should be executed, or if I should be executed, also my flow responder workflow should be executed, the call operation will be called. In our case, it should return a void value because it has been defined as a void flow logic. And it again could throw flow exceptions, anything goes wrong, or it succeeds and returns only creates side effects. So again, we would create a signed transaction, which now creates a new signed transaction flow of the other side, and then defines as an argument of this new signed transaction flow this check transaction, which gets again a signed transaction and could now check the transaction. In our case, the receiver is notified. He could now check maybe whether there was too much money, or I don't know, the sender was somebody he didn't like because he has full access to the signed transaction. So he could now decide to raise an exception if it's not fitting. Yeah, so that gives us an ability to check transactions. But if everything worked fine, we would then call the receive finality. We would create a new subflow, which is the receive finality flow for the other side with the signed transaction and the get ID, which more or less returns the thing with my signature. And then we return null. Okay, so as you can see, this is a lot of code. I think if you walk through it, it's understandable. And you can also imagine that this is type safe, that you can have arbitrary complex objects, you can have arbitrary complex logic, you can factor out the logic into subfunctions, you can use data types, you can use collections. So you have a very, very expressive contract language, but it's really not what you would expect if anybody talks about contracts or programs. Yeah, it's more or less a very, how would you call it? It's very indirect process here, because you create models, and these models are then interpreted by somebody else, so that you more or less have to know how to compose these models of these flows so that you get the right behavior. The benefit is, since all of these things are objects, these objects can also be recorded. Yeah, so therefore people could know what is going on. You can do reflection in the sense that other people could not only simply, you don't call the other flow and it simply is being executed, but it really knows that it creates a subflow, it has another flow, so you get the whole network of these models, and therefore you can make sure that you are part of the right transaction, etc. Yeah, and that's for me, I think, the main reason why they did it like this. so that you more or less have a level of indirection, so that you more or less define what should happen, so that the framework more or less can incrementally enrich whatever you're doing with additional things that have to happen behind the curtain to more or less implement all the necessary heavy lifting of the blockchain. Okay, that's enough to look at this example. Here we have collected some examples, or Susanne and Gonzalo. What are use cases where people said, okay, they build CorDapps in different sectors, yeah, and therefore we created some links to this. We will have a presentation of B3E on insurance contracts, but again, you also have digital identity, capital markets, trade financing, energy, government. These are use cases. Okay, so therefore, I think to conclude, I think the strong point, I think, for Corda is this privacy by design, that you more or less have a lot of control with whom you interact. So therefore, you also have a lot of control of what messages are being sent and how signing is being done. So therefore, also more advanced projects which build their own more or less higher level abstractions can use Corda as a target language. Yeah, because you create it's Kotlin, which is a nice language if you want to develop more complicated things. For example, I was consultant for a company in Switzerland, which developed a successor company to Digital Asset, which developed languages for smart contracts, which should be more user understandable, and they compiled it essentially into the Corda infrastructure in the end. And they also evaluated several other platforms. So therefore, it's not compiling into bytecode, it's compiling into typed Kotlin scripts, which makes it also a little bit nicer because there's some safety done now by the compiler that you don't more or less misinterpret stack values for integers, etc. But again, it's very verbose what you're creating. You also have a lot of parallelism in the system. You have these Kotlin tools and also libraries, more or less, but that's typical in all these things we mentioned in this course. It's also adopted in industry, I think, but initially it's still, let's say, that not, let's say, something like a TensorFlow, yeah, where millions of users use TensorFlow, but it's more or less a niche industry, more or less. Okay, I think that helps you more or less to bridge the gap between my lecture of today and the lecture of tomorrow. And thank you for your attention. And nobody's here to ask questions. And so therefore, we have to postpone the questions maybe to the Slack channel or to the communication with Uli. Okay, thank you very much and see you tomorrow.